Hi everyone. Hopefully no one's too hungover after whatever you all ended up last night. We're going to be listening to Bob talk more about type theory and implicit complexity now.
Okay, thanks, Sean. Can everyone hear me? Good. Okay, so yesterday we got as far as doing the linear lambda calculus and the wrong way to add natural numbers to it. And as I said, let's sure I got the right pen. As I said, what we're going to do is fix this by separating out. That was the wrong point. Separating out the numbers that we get from the input, because polynomial time really depends on what we do with the input and what we how we can use that, from the data that we can construct from the input. So we have to separate, just thinking about just this simple natural numbers type, we're going to have two natural numbers types. One which is nat kind of heavy with a filled dot. These are kind of iterable, but not constructible. And nat with a empty dot. These are constructible, but not iterable. Right, so we've got these nat at the top, which have the eliminator, which I showed you last time. I'll just quickly write up. So again, we have the zero case and the step case. This is now the heavy ones. These are ones that we can iterate over, but the only way we can get one of these nats with a heavy nats is from the inputs. They have to be supplied to us by the input. But to allow nested iteration, we are allowed to duplicate them. So we're just going to assume that there is this apparently dangerous operation which allows us to duplicate these heavy natural numbers. So this seems like it's going to be a little bit dangerous. Since last time, what happened was it was duplication that allowed us to iterate addition over and over again to get multiplication, and then allowed us again to use the same duplication to allow us to iterate multiplication to get exponentiation. However, we're going to be safe because these natural numbers are not constructible. So there's no zero and successor available to us for these natural numbers. So that will stop us from defining addition for these heavy natural numbers. We can't take the input and add it to itself. What we can do is construct these hollow naturals. So these are ones where we're using them just as pieces of data that we can look at, but we can't use them to drive any computation. So we can use this iteration to do things over and over again. These ones, we can make them. With these two introduction rules. And what we do get is a case analysis principle for them. So here, we've got still a 0 case and a successor case, but here we just get access to the predecessor number. We don't get access to the result of recursing on it. So we only get access to whether or not this was a 0 or as a successor. So if we've got a natural number like this, and we want to explore it to a kind of arbitrary depth, we're going to have to drive the iteration using this and then constantly split it apart using this case analysis. And here that's going to lead to some quite tricky, or would lead to some quite tricky programs to write, because you have to always make sure that these natural numbers you've got are big enough to sort of run things with these ones. So we can't even add these natural numbers together without being able to drive it by some fuel given to us by this natural number. And also note here as a first example of so-called additive rule. So here the context is actually shared between these two parts because only one of them will be run. Right, we're doing a case analysis. The 0 and successor cases are mutually distinguished. And so we can share resources between these two halves because when we find out what n is, whether it's 0 or successor, we'll do either this one or this one. Okay. And I'm just going to try and convince you now, so not later on, I'm going to try to convince you that this is sound for polynomial time. But right now, is this even enough for polynomial time? So as I said last time, the way we're going to try and do this is by simulating, well, we're going to assume we have a Turing machine, which is, we know runs in polynomial time. So we're given the Turing machine with its rules. And we've got some type called tape, which is going to be a non-iterable type. So this is going to be some type of tapes that we can somehow look at the current symbol, we can move left, we can move right, but we can only do like finite steps with it. We can only do one little step. So of course, the way that Turing machines work, every individual step is one little finite move left or right or update the state of the tape. So you can imagine implementing this as a pair of lists that tell you what's before and after you in the tape and what's currently under the head. So we can define that kind of type in exactly the same way we did the hollow natural numbers before. And we also assume that we have some polynomial Pn, which will be the number of steps it takes for an input of size n, so a tape of size n, to reach the end of the computation. And now what we're going to do, given this polynomial, we can construct a bunch of iterators which will iterate f that many times using the bits we have so far. So we do this, we do the base case, so an iterator takes a nat, tape. This one's quite simple. This is the base case. This is just going to run the f n many times for the natural number it's given, right? So we did take call I naught, n, and then a t, and then it's going to run f n times. That's just iter, and the base case is the identity transformer in the step case. Okay, and again, I've carried the iterator like that. And then so this does something linearly many times. We can then raise the degree of the polynomial. Oh, sorry, yes, this is the iterable. Yes, of course, yeah. So this is the input natural number. So assuming what happens is that we're given a natural number which tells us the size, an initial tape that we hope has the right data on, and then we run the iteration over the tape again and again and again. Now this is slightly complicated because what we're going to have to do is we've got the natural number, we're going to iterate over it, we're also going to duplicate it and then use it in every sub-iteration. So we're going to have to duplicate over and over again. Yeah. Oh, right. So I didn't define it, but I'm saying that's exactly the same way that I defined this NAT type. You could define any other algebraic data type the same way, as long as you're not allowed to do recursion on it. So I'm claiming that that's a safe thing to do in this system.
When you define type, so is there any notion of duplication or that kind of thing with that? I mean,
You don't, no. So, I mean, to be concrete, you might define tape as something like list of bool, and then a bool under the head, and then a list of bool here, but you're only allowed to check these two lists for whether or not they're nil or cons. So you can step left and right, and you can change the thing underneath. I'm not saying the word zipper, I should say the word zipper. This is a zipper over the state of the. Yes, yeah, so yeah, so exactly the same way. This one is, so this one's special because it tells you the size of the input. This one, you can do it the same for almost any algebraic data type. Okay, so what we're gonna have to do here is duplicate our natural number input over and over again to do all the sub-iteration. So this is just a bit of tedious programming. So we're gonna take the tape. I'm gonna get the type wrong. Let me write the program first, and then I'll compute the type in the way that we shouldn't do. So we duplicate the natural number. Then we're going to iterate. In the base case, we're going to take the input tape and do nothing with it, but also we're going to take the natural number that we're passing through, which is our original input. We're going to throw that away, remembering that we're in an affine situation. So here in the step case, we've got access to the sub-recursion, so the rest of the iteration. This needs to be passed a natural number and the tape. So again, we're going to have to duplicate this natural number. And then we're going to call the recursor with the natural number again. And the iterator, which does these sub-iterations. It's enough parentheses. Right, so what's going on here? In this step case, we've got a successor case. So like if you imagine we're doing the top of the square, we duplicate the natural number so we can go down and do the next level of degree of iterations by duplicating the number. And then we carry on and do the next bit. So this sort of makes multi-dimensional cubes of iterations. Okay, so oh, and then at the end we apply it to n and t. Yeah. Yeah.
What happened to the n prime from the original?
It sits in here. Right, so that's the NAT that we're iterating over for this dimension. This is the NAT which has been sent down for the next dimension. And this is the tape which is being woven. Yes, so we're doing multi-dimensional weaving. Yeah. Okay, and then you can prove that IDN from tape to tape iterates f n to the d times, right? I think. And so once we have this, we can construct the polynomial p by composition, right? So we can composition is going to be addition of how many times we iterate it, and then any kind of extra bits, we just apply f for the final for the constant.
If you pick it off with I1 instead of I2. One. Taking it off by one.
Oh, okay.
Yes.
Yeah,
Or
the
once. Yeah,
yeah,
plus one. I think.
plus one. Okay. Still polynomial. Doesn't matter. Right. Okay, so that's what I'm going to call the cons-free system. So that's a system where I'll try and show later. Every program you can write is polynomial time in the input. In particular, if any program of this type maps to something is going to run in polynomial time in the size of the natural number you give it at the start. Now, as you can tell from this, writing programs in this style is kind of horrible because basically what happens is that we take a natural number that tells us how we can do the iterations, how many iterations we can do and how big the data is. And then we take the actual data we want to process, and then we have to sort of somehow arrange our program so that it iterates over the size and then computes the things we want to compute. And especially in this simply type setting, this is a bit horrible because we constantly have to be thinking about look at the relationship between the sizes of the data in here, how much we want to explore, and the natural number we have here. So before we get to dependent types, which is one way of solving that, another system, which is due to Martin Hoffman. As someone pointed out yesterday, one of the problems with the rules that we had for the natural number constructors was that we didn't pay for them. So we were just allowed to construct zero and successor for free. So one way of fixing that, and this is a really nice idea, is that we make the programmer pay for what they're doing. So we introduce a new type called diamond. And this represents, if you like, a unit of iterability. So we turn iterability into a first-class thing. So before, it was all contained within this NAT, which represented the input. Now, when we iterate over this natural number or whatever we get from the input, we're going to be given the diamonds back. And then we can use those diamonds to construct other nicer data structures that are more amenable to further computation. Okay, so how does this work in typing rules? So if we have a diamond, then we can construct a zero. We're going to use this at thing. So again, we still separate iterable and non-iterable types, but now we can build the iterable types using diamonds. And the successor now is a binary function. So we take our predecessor. And separate resources, we take our diamond. And we construct a successor. So for each of these constructors, we need to pay. It doesn't actually matter. So for the one that's like non-recursive, we could choose to take a diamond or not. And it just leads to off by one errors, depending on which way you arrange things. But for uniformity, we'll just say that every constructor takes a diamond. So now we can't just do that thing we did last time where we can duplicate natural numbers and do addition, because every time we wanted to pay for something, we have to, every time we want to construct something, we have to pay for its construction of the diamond. So we can't do the duplication function from before, because remember that iterated over one natural number, but generated two, and that's going to mean duplicating our diamonds. So in fact, I'll show you how it works in the iterator. So now, in the zero case, we're given a diamond to construct the A. And in the step case, the sub case, we're given a diamond. And again, we have a whole natural number. So if we compare this to the previous one, we've added these D variables to the zero and successor cases. So we're given diamonds as we iterate through the data type. So we, yeah.
How do you construct the diamond? Like what are the introduction rules?
Iter.
Repeat the question or.
Oh, yeah, sorry. So the question was, how do we construct a diamond? And you do not construct diamonds.
No, you get them from Iter.
Iter?
Iter.
Iter, yeah.
Iter,
Oh, yeah. So you do not construct diamonds. There is no introduction rule for diamonds in the same way that you can synthesize them, but let's say in fairy tale land, you cannot construct diamonds. One finds them in treasure troves. And we get them from the input. So we're still given the input as this heavy natural number. We iterate through the natural number, but that gives us diamonds as we do it. So if you imagine Sonic running through the maze and then rings and so on, we get diamonds as we iterate through the number. And the key point now is that we can add further algebraic data types where we constructors we pay for with diamonds. So we can iterate through the input, gather the diamonds, use that to build other data structures which then we iterate over. So we have a more flexible.
Discovering big things.
Yes, yeah. So there's no introduction rule for diamonds. We have to discover them.
But they're very hard and can be recycled forever.
Yes. But we are allowed to lose them because we're in an affine system. So we can. Yeah.
You can also add any multiplication for the diamond, right? So
Multiplication?
I can ask for like 6 diamonds per natural number.
Yes. Okay. Right. So
you can just repeat it.
yeah. So the question.
The comment.
The comments where Connor said the diamonds are very hard and infinitely reusable, which is true. So we put them into these data types, we get them back out, and we just dust them off a bit, and they're fine. And Ohad said, I've forgotten.
You can get any number of diamonds by duplicating the natural numbers, right? Is the point. So
no,
just get one.
Where we can't duplicate these natural numbers. So yeah.
No, the heavy ones I can.
Oh no. So in this system there is no duckmat anymore. So this is the price. This is the price we pay.
But
Because
if
then
you
we
ask
could-
for like 4 diamonds per natural number, right? I could do that, right?
Yes.
Yeah.
Right. Yeah. Okay. So I will add some comments to this.
Sorry about that.
So we could change, this says every constructor is worth, the comment was we could add multiple diamonds to every natural number. So Martin Hofmann, being a very clever man, noticed that this has a striking similarity to the technique of amortized complexity analysis, where what happens essentially is that rather than trying to directly count the steps as you're doing something with complexity analysis, you conceptually store some potential in the data structure. So the data structure's shape or structure gives you some sort of complex, some sort of payment that you can use later on. And what we're doing here is we're storing it in the data structure and then we're freeing it as we go. So I just want some comments. So this system works in polynomial time. If you have a system where you actually get back fewer diamonds from doing iteration than you put in, so we can have one where we can pay, say, n+1 diamonds for construction, but get n diamonds back. Then we're back to linear time because we're paying explicitly for every time we go around the loop with a diamond. Another interesting thing, again, noticed by Martin, is that I've used this @ symbol here. You can actually think of the diamonds as pieces of memory. And again, if you then say we don't get the diamonds back, oh no, we do get the diamonds back, sorry, and we pay for them, we can actually think of this as the place where we're going to put this constructor into memory. So we can actually implement the system without using malloc or any kind of garbage collector. Because when we construct each constructor, we put it in the slot represented by this diamond. Each diamond is a memory location. And when we deconstruct it, we get the memory location back. And because we're being linear, we know that we're not going to use this one again. So you can make an entire sort of functional programming system where everything is in place update, and we never have to run the garbage collector. And this idea has been picked up again recently by Dan Lyon and Anton Lorenzen, where they've implemented it in, I think, the COCA system, and sort of pushed it a bit further. This is quite a nice system where if you want to do functional programming without a garbage collector, you can use these rules and forget about polynomial time, but treat this as an in-place update. So yeah, you can do if diamond equals memory location, then okay, so actually the next thing in my notes was to do the completeness proof for this system, which I should say this system is called LFPL, which just stands for linear functional programming language. So it's not just kind of the most plain name you could come up with for a linear functional programming language, but that's what it's called. So LFPL is any kind of this kind of system where we pay for construction with diamonds and we get them back when we iterate. Oh yeah, we get linear time. I should also say that what you can then do in this system where you don't get back as many diamonds as you pay, you can then turn this into an automatic analysis for functional programs to how much complexity they use, because we can annotate the types with how many diamonds they have. And then some work that started with Stefan Jost and Martin Hoffman, it was later carried on by Jan Hoffman, who was Martin's PhD student, but has a different number of Fs. You can then use linear programming to infer the amount of diamonds that are distributed throughout the program. And this gives you quite a powerful technique for inferring the costs of pure functional programs. Okay, so this LFPL idea is extremely powerful and can be used for several different techniques. Oh, and finally, I should mention, you can also use this for imperative programming. So in separation logic, you can add a diamond proposition that represents a piece of resource that's going to be used that isn't memory resource. And then you can store these in data structures and use them as well. Okay. So I think we're halfway through. So I was going to do the completeness for LFPL, but I think I'll skip that. The only interesting thing is that rather than this one where you get the plain n to the d or d+1, in the LFPL one, the iteration shape we make is actually a triangle because we have to reconstruct the natural number one less than the one we get on each iteration. So we actually end up with an iterator which does n choose k iterations. So we end up with triangles for Pascal's triangle. Okay. So I've shown you these two systems. One I call the cons-free system, so we're not allowed to construct anything. And the other, the LFPL system, where we can construct as long as we pay for it. But how do we show soundness? So soundness is going to mean that if we have a closed term, type nat to, let's say, bool, bool is going to be just something we can, it's got true and false constructors and we can do if then else on it. Then there exists a program, let's call it EM, such that when we evaluate it, with our EM, such that for all n, we evaluate that, and I'm going to be a bit vague here because I'm going to to some Boolean in k steps. There exists a program and polynomial p Right, so there exists a program and a fixed polynomial such that for any input, when we evaluate the program with the inputs, then we get some Boolean in k steps such that k is less than the polynomial for that input. Right, so this is going to be the full soundness property. And the way we're going to prove this is via what's called a realizability semantics. So what I'm going to do is take a,
Yeah, about the last slide.
Right.
I was wondering, now that we have all these new rules for the what's it called, this natural number type with the built-in dots, do we still need the other natural number type?
Oh, yes, yeah. So yes, we still need the other natural number type and all the other non-iterable things, because we're still going to have to be able to construct data which isn't iterable that we don't have to pay for. So we still want to be able to do that. We actually get a slightly weaker system. So in fact, the completeness proof doesn't work because we wouldn't be able to represent the tape, because we'd, the tape would have to be the same size as the input we were trying to do. So this, in fact, another way, another interesting property of this is that because the diamonds are preserved, every function is going to be length preserving in some sense, which I'll get to quite soon. Right. So we're going to prove soundness by a realizability construction. So what does realizability mean? Roughly speaking, what we're going to do is interpret types as sets and terms as functions, as was sketched by Chris the other day. Yep.
So it's about the statement. So you're saying that on the first line that M is a term of type that like nats dot bool, and it's a term. It's a term in the formalism, right? So like then there exists a program EM like what exactly is that formalism EM exists like when you say?
Right. So I'm gonna So there's lots of missing parts here which I haven't explained. So one is yes, there is some other formalism of programs which have a costed execution, which aren't the terms. The other thing is that what's the connection between EM and M? Do they compute the same thing? Right. So this is what I'm going to sort of cover now with the realizability. So realizability consists of
Sorry, can I just ask a question before you continue? It's just about this Boolean. I noticed that unlike natural numbers, it doesn't need to be split up into a black dot and a white dot.
Because Booleans aren't is not a recursive type, right? Yeah, so enums are fine. Or in fact, enums with arguments are fine. Yeah. So yeah, we can't go wrong by having a look at a Boolean because it won't give us any more iterative power. Right. Yeah, so said there's EM comes from some other formalism, which I haven't defined yet. And what is the connection between M and EM in terms of like, does this compute the right Boolean? So realizability, what we're going to do is, like, first we could interpret the calculus in a semantics where all the types are interpreted as sets and all the terms are interpreted as functions. And this would tell us semantically what it's meant to do in a kind of input-output sense, right? So we can interpret nat as the natural numbers. Also, we interpret the hollow nats as the natural numbers. And we interpret.
That's hollow, right?
Yeah, I know. Oh, yeah. As just the functions from A to B. Right, and this would give us a sort of cheap and cheerful semantics for the extensional behavior of the program. So it would tell us that if we put in a natural number then there is some function that tells us what we get out at the end. So we can use this to reason about these programs being equal. But it doesn't tell us anything about the kind of intentional behavior. So what happens to actually between the input and the output in terms of making it compute. So what we're going to do is glue on sort of low-level information onto these onto these set theoretic elements. So in summary, we assume some formalism of abstract computation. So I don't want to go into the full details of this because it's just writing out lots and lots of rules, but let's just assume that there are some set of programs curly E are expressions and values V, and that we have some kind of evaluation thing. And for now, we'll uncost this. So it's just going to be to prop. So this says if we run this program on this input, then we get this output, yes or no, or yes or constructively. So this is just some kind of evaluation relation. Yeah.
Now you're talking about like,
Now you are like talking about this new the formalism with like diamond, right?
Oh no, well, right now I'm being high level enough that
Yeah.
it's going to talk about both, but yeah.
Yeah, like I mean, you're proving the soundness of this LFPL, like you define.
Both of them are the same.
Okay, so earlier you showed something right with the Turing machine, like the tape and
Yeah.
So for that you give some like it felt like you define something and by constructively you show that it is of polynomial time earlier.
No, so this one we're assuming we're given a Turing machine with a step function that's f and a polynomial which tells us the maximum runtime for any input.
Okay.
And we're constructing a program.
Yeah.
But you could do this in any type theory, well, any time theory, it's got these data types. So that would show you that it's at least polynomial time. So that's what we're doing. Right now, we're going to show it's at most polynomial time.
Oh.
Yeah. Okay, so we're going to assume some set of programs E and values V, and just for now, we'll do it uncosted. And then what we do is we redefine types. So it's a set of the extensional or mathematical values paired with a relation. So a type is there's A, which is a set. And there's a realizability relation, which is a subset of values and elements of the set. They're mixing up formalisms, but okay, so we have the set, which is the set of values. So for a natural number type, that is going to be the natural numbers. And here we're going to have a relation that tells us that this value is an implementation of this mathematical value. So we might have in our set of values here, we'd have the implementations of all the natural numbers. And we'd say that they represent these, but we might also have implementations of functions, the closures which represent the functions. And we'd say that we'd define this relation to say this is a good value for representing this particular function. So a type comes with information that tells us about how it's represented in the machine. So this is the kind of semantic component, if you like, and this is the implementation component. And we've got a relation that connects the two. So every type tells us how it's implemented. So one thing is we can have multiple types which have the same carrier set, but different implementations. So that's going to happen with these two. And in particular, we can express things like erasure. So things which only appear in the semantics, but don't appear in the implementation. They're always represented by some sort of trivial value here. So we can sort of express things like erasure. And then what makes it go is a term A to B, or A. Yeah. Is a function from A's to B's. Right, so this gives us the semantic component of what's going on. This tells us that if we stick this A in the inputs, then we're going to get this B in the output, such that there exists an implementation in our set of programs such that for all, run out of space, A and V, such that V implements A, then there exists a V prime such that evaluating such that V prime implements F of A. That got very small. But I'm gonna move this. Such that there exists program in E so for all A and V. So this is all semantic inputs and their implementations. If V is the implementation of A for big A, then there exists a V prime such that evaluation of E with input V gives us V prime, and V prime is the realizer of the output. So this is actually a surprisingly compact presentation for a thing that tells us two things. One is, if we have an implementation of the input, then we get an implementation of the output. So we're saying that evaluation correctly tracks what's happening. Also, it also says that the evaluation is total. So every function is going to be realized by something which always terminates. So as we build up denotations of terms, we're always going to maintain the fact that our programs that we construct are ones which terminate. Also, if you read this constructively, what I'm really going to be doing here is writing a compiler, because every time I construct a term from A to B, I have to give the program that does it. And usually I'll construct this program for whatever programs I'm assuming at that particular construction point. So the whole semantics at the end does a correct by construction compiler of the system in a way that's also going to maintain the costs. Okay. I just want to quickly give two examples before moving on to the more complex one for the what's the question? Two examples before moving on to the.
I was wondering, why is it an existential quantifier on the V prime instead of universal one?
Because we're saying that for any input, there must exist some outputs that we get to. If it was a for all, then it might be that there is no output.
But it's okay if the compiled program also generates outputs that are outside of the interpretation of B?
Yes, that could be so. So I suppose I'm assuming here that eval is deterministic. But,
Okay.
Yeah, which it would be. Yes, if eval is not deterministic, then you might have to say there exists a unique, or that there exists at least one, and for all of them, who does the right thing. So examples. So one easy one is we let our values be natural numbers, and the programs are just the one element set. So we've got no interest in programs, but our values are natural numbers. And this gives us a way of recording the sizes of things. So this will mean that, so if we let V be natural numbers, E be just star, and then eval.
Sorry.
Yeah.
So you said we're constructing a compiler, but this is an existential, so not necessarily.
Yes, okay, so if you read that existential as a sigma, then we're constructing a compiler. However, I want to consider two terms equal if only on the F part. So yes, so we have to, yes, there's a phase distinction going on here where, so two terms are equal if they're equal on the F part, and we just say we don't care what the E is. But if we're treating this as a compiler, we do care what the E is because we want to get it out at the end. But in terms of reasoning about programs, they're just equal if the F's are equal. But here's one where it's not deterministic, but here we go. So now the evaluation is for a program, the trivial program, we can evaluate from n to n prime if n prime is less than n. So we can throw resource away, but we can't build extra resource. So we're treating these implementation values as the amount of resource that's being used up in this type. And then we can define nat heavy to be the natural numbers paired with the relation okay, so here, this is the value that's the implementation, which is the size, and this is the actual natural number. And all we need to do is say that the size that's accounted for by this natural number is bigger than the actual natural number itself. But it might, because there's a bit of slack, it's useful later on. But the hollow natural numbers don't take any size at all. They're allowed to consume, pretend they have taken up some size, but we're not allowed to assume that we have any size from them given their actual content. That's the wrong. Okay, so these heavy natural numbers, the size associated with each one is at least the natural number itself. So if we iterate over it that many times, we're going to have this much resource to use up. This one, the size associated with it is just some arbitrary natural number. So this allows us to sort of consume extra resource in some places if we need to. Yeah.
So it's just n times n.
Yeah. So yes, so the question was this is really just n times n, this relation.
Is it immediate that every type can be interpreted as a set? It's a set as in set theory, right?
Yes.
So
oh, yes. So in this system, yes,
Okay.
because we can do the function types are going to be functions, the tensor types are going to be pairs, and the natural numbers are going to be natural numbers. And any of the algebraic data types we add, as long as we only allow strictly positive, would be fine. Yeah.
So
Yes. Yeah, so there's absolutely no recursion going on. There's no local state going on, anything like that. So we don't need any domain theory or Cauchy or anything. Yeah. Okay. So the first example, the second example. So this one, the programs here were trivial, but we were just recording our resources with the size. Oh, I should know. I just want to do A tensor B. So what's this one going to be? This is going to be pairs of A's and B's. And then. Right. Okay, so this is so showing us how the resource actually splits up between some of the types. So if we've got this tensor type, then the semantic values are just pairs. This is the Cartesian product of the two sets. But now, if we've got a total resource n that's to be split between A and B, then we do this convolution or day product. We say there exists two resources N1 and N2 that add up to less than the original. And these resources are sufficient to support or implement this A, and the other resource is sufficient to implement the B. Right, so this tells us now that when we look at an A tensor B, we get two separate resources. And if you think back to the separation logic lecture yesterday, this is extremely similar to the separating conjunction in separation logic, right? This exactly says there are two separate heaps that add up to the whole heap, and the two separate heaps support the two halves. This is a sort of key definition in any kind of these kind of resource conscious systems. Yeah.
So this is not a product, right?
It's not a product. This is
there a product?
Sorry?
Is there a product?
There is a product. Yes. So again, it has the same. Right, so now we share the resources between them. We say N implements A, the product AB, if N implements A and N implements B. So now if you want to be resource preserving, we can only use one half of this product. So this is the key rule for additives in linear logic. We're allowed to do projections, but if you project one half, we can't use the other half because you've already used the resources for it. This says that, yeah. So there's two different ways of sharing the resources between these two things. But notice they have the same underlying sets, but different resource specifications.
Did you close the parentheses? I'm not one about.
I'm not about. Okay, I've got a little bit of time left, so I'm going to finish with, so that was a resource-aware semantics using realizability, but the programs were trivial. Next time now, I'm going to have to go on to the resource-accounted one that's going to combine these two examples, but let's do example 2. Which is just enough to get us a category out of one of these realizability things. So let's assume that expressions and values are the same thing, and they at least contain a B and an I, and there is a application such that this is going to be the basics of combinatorial logic. Such that these equations hold. So this is like a BI algebra. This is just enough to get us a category because we've got the one that does composition and the one that does identities. And then if we've got a term, we've got Let me use different letters. Let's say we use X and Y for types. If this is realized by some alpha, this is realized by some beta. Remember, term is realized by some program, G is going to be realized by some program, then the composition G after F is going to be represented by B dot beta alpha. Because then when we apply it to the argument, then the first equation will kick in and we'll get the composition of the two functions. And ID XX is represented by the I combinator. Right, and so any kind of set of things which can do computation, which at least includes the B and the I combinator, we always get a category. And then if we add, so this is enough for a category. If we add C,
The symbol upside down.
Yes.
yeah.
Wrap up in about a few seconds. We're a minute over, so.
Yeah, sorry. If we add C, then we get products. We get tensor products. And what do you call it?
Associates with one.
Yes, yeah, yeah. So it's function application. Yeah. So this is the swap combinator, right? This takes a function, two values, and opposite arguments. Okay, so I've finished there. Tomorrow, I'll get on to a specific instantiation of realizability, which will prove polytime soundness. Okay, good.
Goodbye.